We're ready to start back up. The talk before, and Rich talking about heterogeneity, is quite appropriate because that's something that Sonya does day in, day out, and was probably quite concerned about. And given that there's more machine learning and ML and AI being used in cryo-EM, it's, I don't know, it's becoming easier or even more challenging because there's so many tools. So Sonya's coming from the Flatiron, and I just talked to her. Maybe it's because it's Oscar season. If she wasn't a scientist, she probably would have been a screenwriter. So I'll let Sonya do that.
Cool. Thanks, Ed. Well, I'm happy to be here today talking to you guys about these computational methods for heterogeneity in single particle analysis. As Ed mentioned, I'm at the Flatiron Institute, and we're an entirely computational institute down on 21st and 5th in Manhattan. And it's a great place to work. And as he said, we focus a lot on these computational methods for cryo-EM. And Rich gave a good introduction to some of the things I'll talk about, but I'm going to talk much more about really the nuances of what we have to think about when we try and approach these methods, and also when we're trying to develop them. And so a rough outline of what I'm going to talk about is here, right? Some ML methods, but then also some practical considerations when you're using continuous heterogeneity methods, and also something that we're passionate about at the Flatiron Institute, which is combining these methods with molecular dynamics simulations, and then finally how we assess some of the performance of these methods, which is on our mind a lot, especially as we have exploding numbers of these methods, and we're trying to figure out, do they give us the same answers for these different data sets, and can we trust them? And so this is definitely something that's an important thing to consider. And so, there we go. Yeah, and just before I start, a couple of useful reviews to check out that are along the same lines of what I'm going to talk about today is this review in Current Opinion in Structural Biology from last year that we put together also with Ellen Zong. It kind of goes through these different paradigms of how to get conformational heterogeneity and probability distributions out of single particle cryo-EM. And then another one that's not from us, but I found very useful, is from Nina Milani's group at UCSD. And this focuses more on machine learning methods and the different approaches they take, and also the different paradigms they take within just a neural network framework, which is surprisingly diverse. And I'm not going to go into all of those details with you today, but if you want to know them, they're available in this review. And so, as Rich mentioned, before cryo-EM, the main method that we were able to get high-resolution structures from was X-ray crystallography, where you're really limited to a single structure of your molecule because it has a crystal packing that really makes this an essential part of getting the structure at all. But for cryo-EM, we have our individual molecules in our thin layer of ice, able to adopt really any conformation they choose once they've been vitrified, and allow us to really understand much more about the conformational dynamics, as we've seen even from methods of discrete classification. We can really access very interesting conformations and new states that we really weren't able to access before, and also even be able to get structures of molecules that we couldn't access with X-ray crystallography. But despite the success of cryo-EM since the resolution revolution, there's still key advantages of this exact feature that are yet to be fully exploited, namely this conformational heterogeneity, and especially continuous conformational heterogeneity, where you can imagine you have a hand or many hands all wiggling in a similar way, and you take this frozen snapshot of them. Often what we actually get in cryo-EM is an average structure of this hand. We don't get a good sense of what is actually the dynamics of these fingers, and we lose this information in a lot of the existing standard reconstruction methods. And what we often end up doing is actually even discarding particles that belong to conformations that we're not interested or don't give us the very high resolution particle. This is a relatively old scheme of 3D classification, but the concepts are still the same, where we really only use a small fraction of the initial particles that we have to get the final structures that we're looking at. And I think a fun example of this comparison of crystallography and cryo-EM is this paper from John Hunt's group at Columbia from a couple of years ago, where they look at this this enzyme. And actually, most of the paper is about a crystal structure of this enzyme, but there's one figure that goes through a cryo-EM data set where they really rigorously show that you can see many more dynamic conformations, not just this symmetrical tetramer in red, when you do cryo-EM. And this actually allows you to potentially get information about the actual function and enzymatic catalysis of this protein, which you really were not able to access with the exact same sample in X-ray crystallography. And so now I'm going to start going through a few of these various methods. One of the more simple ones is a principal component analysis for continuous heterogeneity and single particle analysis. And one of the more famous applications of this, though actually if you look back in the literature, you can see lots of different applications trying to get at similar things, pretty much like way further back than this if you really want to find them. But this is a nice example from Holger Stark, where they do principal component analysis and are able to distribute these conformations of the spliceosome along this PC space. So this is a nice tool, but it has some limitations, and I think we're still not fully I think the field still doesn't fully agree necessarily on what the limitations of this kind of approach are. So for example, Carlos Oscar Sorzano and Jose Maria Carrazzo have this paper from 2021 that says that PCA is limited to low resolution analysis in cryo-EM. But more recently, a postdoc, Mark Gillis and Amit Singer's group, has this preprint up that has a Bayesian framework where actually it's still a PCA-based framework where you show some really amazing results extracting out continuous heterogeneity from cryo-EM data sets. And so this is still a preprint, still somewhat preliminary, but I think this is a very nice case of how there's still lots of things we don't understand about how to use these computational methods to extract continuous heterogeneity from these methods. And so I'm kind of going to start going a bit chronologically here. Started with PCA because it's one of the ones that's a little more simple to think about. But one of the most early methods for getting at continuous conformational heterogeneity from cryo-EM is this manifold embedding, or more recently manifold EM method, which came from Abbas Ormaz's group in Wisconsin and Joachim Frank. And here in this initial presentation of this method, they were able to analyze an aporibosome and see it wobble along the low energy states here in blue through various conformations that previously weren't accessible, especially from an aporibosome. And here they can see them, though in still relatively low resolution. This is in 2014. And think of the ribosome as this Brownian nanomachine that wobbles between these states. And this was a really amazing work when it first came out. And since then, some other applications of manifold embedding have been done. For example, here with Amédée de Georges' group, applying it to the rhianodin receptor here. And instead here of just looking at an APO data set, they have an APO data set and a ligand-bound data set. And they're actually able to find a trajectory of the conformational path of the molecule between the low energy APO state and the low energy ligand-bound state. And through this analysis, they can see that the conformational change they get from this is not just what you would get from a simple linear interpolation here in red, but actually follows a non-trivial path along conformational space. And here this is looking at these two distances within the molecule. And here just to, I'm going to skip forward probably. And here just to show a movie of what this looks like, of this transition from a side view along this path. Although I will say this movie itself is somewhat of a tour de force of a lot of people working together. There is some molecular dynamics simulation involved and lots of manual work in getting the manifold embedding code to get you these kinds of results. And this code itself is written in MATLAB. And so it really takes a lot of people working together to get these kind of results, in this case in 2020. And this slide kind of talks you through some of the heroic effort that it took in those days to get at this kind of a conformational landscape of a molecule like the ryanodine receptor. And part of the benefit and curse, I think, of the manifold embedding method is that it works on these clusters of projection directions, so just basically these 2D projections, and does this manifold embedding analysis for each 2D projection direction individually, and then you have to stitch. So in those two papers I showed from PNES and Nature Communications, they actually manually have to look and see if the movies they get out of these conformational changes, and in this case they had hundreds of different projection directions, if those conform to the same conformational change, and stitch those all together to get your final conformational landscape and transition. And the process of how this happens, you can read these papers that show, initially there's a Euclidean distance that's measured for the particle stacks in each projection direction, and then diffusion mapping step, which is also something we often use in molecular dynamics. And then in order to take this manifold space and project it back down into these movies, which we can actually look at, we use this nonlinear Laplacian spectral analysis, which was actually initially developed, here you can see this paper in 2012 for, doesn't say in the title, but for actually looking at modeling the weather. And so some of these concepts of how you look at dynamics have a lot of different applications across different scientific fields. And here, this method was borrowed from there. And so as I mentioned, in those two papers that apply this method to the ribosome and the ryanodine receptor, this stitching together of the projection directions was done manually, but more recently, Suvrajit Maji has a paper out that uses this computer vision method called optical flow to actually do what you normally do by eye and automate this process much more. And I will say at the Flatiron Institute, we have ended up taking on the software development of this tool. And so now it's in Python, and this optical flow method is implemented. But I think it's still not as user-friendly as some of the other methods I'll talk about today. But if you're interested in this kind of thing, you're welcome to talk to me. Yeah, and so we're working on making it easier for other people to get nice movies like this from the manifold embedding method for their projects. So continuing sort of along this pseudo-chronological timeline, actually, Rich already mentioned this method of multi-body refinement from Relion. And it did come out after the first manifold EM paper, but it was much, because it's implemented in Relion and allows you to look at these conformational changes. And again, this uses PCA. It was a kind of an exciting thing to come out and to allow people to look at what kind of conformational changes different domains have with respect to each other. I don't know, I think that there's things like CryoDragon now that I don't know how much people actually still use multi-body refinement, but I think I don't know, maybe you guys even know, I don't know. But I think for specific problems, it's still nice and has fun properties. But yes, also, as Rich also mentioned, in 2021, the first neural network approach to trying to solve these problems in continuous heterogeneity for SPA came out. And here, what Ellen Zhang was able to do is build this particle image encoder decoder, volume decoder, which is just a self-supervised variational autoencoder that actually outputs all of your images on this latent space. And it works, as Rich showed, for both compositional heterogeneity and continuous heterogeneity. And so this was a very promising method, and it is relatively user-friendly, especially for people who are familiar with Python and can download things using Conda or pip. And it also has a nice set of Jupyter notebooks for which you can explore your data sets. So Ellen actually now has her own group in Princeton and is developing more methods on top of CryoDragon, which I'll talk about a little bit in a later part of this talk. But I think there are some known questions still involved in what CryoDragon is able to give you. For example, if you run it multiple times, the results are somewhat stochastic, so it'll give you maybe a slightly different latent space embedding of your images. And the other thing is that we found for CryoDragon, sometimes it really emphasizes compositional heterogeneity versus conformational heterogeneity. So, for example, we have one sample where we have a toxin bound, and this was very difficult for us to see the other conformational heterogeneity of our sample when we were just kind of seeing this toxin binding and unbinding. And so there's still lots of things to figure out, even though CryoDragon has been, I think a really nice advance for this field and really pushed the rest of computational people in this area to move things forward. And so that same year, actually, CryoSpark came out with 3DVA, which again, Rich talked about a bit. But one thing that this brings up is one of these questions I brought up earlier, is that 3DVA does restrict you to this linear motion, and some things in biology are very well described by these linear motions. But one of the benefits of CryoDragon is you have this multidimensional latent space that you're not really restricted to just what you can see in like one single linear space, or a set of these linear spaces. So I think these are all the questions that we're still trying to ask ourselves, or what is the right space to really allow us to represent our molecules correctly. And so another paper that came out also in 2021 was this Gaussian mixture model method from Stephen Ludke's group, and it's also implemented in EMAN2, if you're an EMAN2 fan. One of the advantages here is that it incorporates this Gaussian mixture model framework, which means there's lots of little Gaussian dots that actually make up your volume instead of just representing it in a full voxelized volume space. And this allows you to look at the motions of these individual Gaussians much more precisely to get at the conformational heterogeneity, which I think was a really nice addition by Muyan Chen, who's also continuing to do some really good work in this space. And it kind of pushes us more towards the area where I like to think about in molecular dynamics, of more towards atomic and molecular information with these Gaussians. And so after 3DVA, CryoSpark came out with this much more complex tool for continuous heterogeneity analysis, 3D Flex. And here you can get at much more complicated motions than you can get at for 3DVA, but it actually takes a huge amount of computational power to train, we found, and there's lots of hyperparameters to tune. And so the way this method works is it develops a canonical 3D map, which it then deforms with this flow generator network that it constructs. But the purpose of this method is actually to develop a higher resolution canonical 3D map. So even the developers themselves will say that you probably shouldn't trust the motions that 3D Flex is giving you from this flow generator. I think sometimes looks right, but I think that they actually have no idea if the motions it's telling you are correct or not. And part of that is one of the things that I already talked about, is how do we assess these models? How do we even understand when these motions are correct or not for all of these methods? But I think it's, to the credit of David Fleet, who I think I've talked to more about this, is that they are very interested in figuring out to the extent to which you can trust the results of 3D Flex. And I think part of that also would involve how to choose these different hyperparameters when you run these methods, and how to choose them correctly so that you're not over-biasing something to see something that's maybe less correct. And so just to show a fun movie of one of my favorite proteins that this gives us, seeing this kind of sent me down a wild goose chase of trying to figure out if these motions are real. I will say I think now we do think these motions are real, but I think that everyone kind of has to do that journey themselves for whatever molecules and results they get from 3D Flex. But you can see that for this method, you can see, not high resolution, like you can see interesting conformational changes, though you can't necessarily see side chain conformational changes. These are things that are of interest to a biologist who wants to know what are the relevant states of their molecules, what's the relevant ensemble. Sure. Yeah. Sorry, I can't hear.
How to use the neural networks inside, which sets the particles put together. What was
Yeah, so they have this consensus map, right? And then they have all of the images all of the particles that you're using, that you put into the neural network. And what it's trying to do is develop this flow field of your consensus map to give you, I feel like I'm just repeating what I said, so I'm not sure if it's clarified, but yeah, basically that's part of the algorithm, is deciding where the motions are that actually result in giving you a higher resolution consensus map. And so yeah, it's a little bit convoluted, but it seems to work really nicely for some things, and the movies look amazing. You can look at the other molecules that they have that go through this. There's a really nice ribosome movie that I didn't put up that I maybe should have. But yeah, I think that's the part of the power and the drawback of this method is this loss function that they use to trying to make the canonical 3D map higher resolution. And yeah. Yes, and so more recently, October 2023, Relion also now has a new machine learning based solution for this heterogeneity problem. But similar to 3D Flex, Shores himself on Twitter admits that he also shows model bias can be nasty when modeling molecular flexibility with many parameters. So this is still a problem that the field basically doesn't really know how to solve, is all of these parameter choices when you're looking at these methods for looking at continuous heterogeneity in cryo-EM. And here this method is called Dynamite. I think it's only a preprint right now on bioRxiv, but it has a somewhat similar architecture to the 3D Flex with these displacement fields. One nice thing I actually like about what they've done here is it does have a method for error estimation of the deformations, and I think this is a really important aspect of these methods that we should be considering more carefully, and I'm really glad that they've done this here. And it does seem to be implemented in Relion 5. I personally have not used it, I will say, but I'm very interested in anyone who can give me an experience of how it works. And then there's now many other methods, including not just in Relion and CryoSpark, not just CryoDragon, but also available in tools like Scipion. So Scipion, if you want to look, I think there's 8 different methods for continuous heterogeneity in their package. I've just shown 2 of them here. One is this 3D Zernike polynomials, which uses these Zernike basis sets to find your deformation space. And another is more based on actually integrated with molecular dynamics simulation from Slavik Ionik's group called MD Space, also fairly nicely implemented in Scipion if you already know how to use that package. But the field is like really exploded. Some of these papers are from the last 6 months. Here there's a paper from December 2023. It's actually from ByteDance, which is TikTok, and it's called CryoStar. And actually, we really like this method. It's a method that's been actually able to incorporate atomistic and molecular models into what's actually somewhat similar to the CryoDragon variational autoencoder. But so far, they seem to have really nice results and done a good job. I didn't even know they were thinking about these problems, but thank you, TikTok. And then there's also something that came out just last month, Cowscape from Holger Stark's group, which is more back to this PCA type methods that I talked about at the very beginning, the same group, actually Holger Stark's group, but now they have a much nicer software package to allow people to use it in a more user-friendly way. Yeah, and so as I mentioned, there's lots of practical considerations when you're thinking about using these methods for your individual project. One is that most methods take in particle stacks after you've already done 3D refinement in a previous tool. So here, you already have, usually it's best to have extracted recentered particles where you already have the poles, the Euler angles, and even the defocus estimates. And so all that work should already be done for you ahead of time, and then you can put it into these methods. Generally, this can be tricky depending on which tools you're using. Sometimes it's extremely user-friendly if you're using CryoSpark or Relion and you're just using their existing tools inside. CryoDragon is a little bit more friendly with CryoSpark inputs. Manifold embedding is a little more friendly with Relion inputs. And the original manifold embedding was written for Spider inputs, which I don't know many people use Spider anymore. But I think for a lot of tools, it's actually fairly easy to get your input data in the right format to put into these various heterogeneity tools. Another thing is related to this is that procedures to jointly optimize both the poles, that is the Euler angles, your rotation estimations, and the conformation of your protein are still in the process of being improved. So CryoDragon has, CryoDragon 2 ab initio, which does the pose estimation itself, but it actually does a very computationally intensive brute force search. It's not using maximum likelihood, and there's a lot of questions about really how to do this properly in a computationally effective way to jointly estimate both your orientation and your conformation of your sample. And so they also have a more recent paper out here. This is CryoFire, which has used this amortized inference machine learning framework to tackle this problem. But in practice, if you look at this paper, the results for CryoFire and CryoDragon 2.0 are pretty comparable. So it's still definitely something that's a problem that we're trying to do better at solving. And I think that's just going to come from doing the math and figuring out the right way to do this in an intelligent way. For example, and I'm not really sticking to my chronology anymore, but so CryoGAN, which is a generative adversarial network for this problem, for 3D reconstruction itself, has this very nice framework for this, where it's actually trying to use this adversarial training and allow you to do the pose estimation inside the neural network itself. But in practice, CryoGAN gets stuck at relatively low resolutions. And so this is a nice paper as a proof of concept to show that you can start to use these machine learning methods for this problem. But it's still really getting all the way there. And I will say this isn't just, oh, we want to see if machine learning can solve this problem that Fred Sigworth already told us how to solve. I think part of the issue is that as we get into more complicated samples, like tomography, for example, really trying to harness the power of machine learning to solve this problem along with all the other problems that need to be solved will prove to be a fruitful effort. For example, I've anecdotally heard of experimentalists who know their protein is structured, but it's so floppy they can't get a consensus reconstruction. And basically these methods currently are still relatively hard for us to approach with these machine learning methods because of this problem. So if we can start to solve this problem computationally, then that will make basically whole classes of samples newly accessible to us possible. Yeah, so another issue to consider for these continuous heterogeneity methods is that if you have a membrane protein with a nanodisk, this can sometimes obscure your protein conformational heterogeneity. Here I'm showing an example from manifold embedding because it's very clear, but we've also seen similar things happen in CryoDragon, and have talked to Ellen about solutions to this problem. And she has thought about potentially having another neural network that learns basically the conformation or the conformation of the nanodisk around your protein while also learning the protein heterogeneity, but it's another problem that's not very high on the priority list right now. So basically what we have done for problems like this is just add a mask for signal subtraction, but this is not a perfect solution. I will say we still see a lot of artifacts when we do this in these methods. And yeah, and also something I want to note is that this isn't necessarily a function of the size of the nanodisk as it looks here, but what we think is that it's actually the protein being in different positions of the nanodisk, and this basically reads as the nanodisk shrinking and growing, but I think the nanodisks are of relatively consistent sizes. But I think this is something, that we've seen so far. Well, I think it depends on exactly how you're building your nanodisk, but I think in this case, at least Yufan Cheng was saying this is what he thinks is happening. Yeah. 30%? Okay. Yeah, I mean, then maybe it's.
And they also vary in shape.
Yeah.
And if you symmetrize it, you're going to end up with all sorts of artifacts because the nanodisk doesn't obey the symmetry.
Yeah.
A lot of times you'll see the protein, this is the disk, the protein sits on the side, it doesn't sit in the center of the disk.
Yeah.
And so this sort of fourfold symmetrization and then triangular aligning it will cause all sorts of artifacts because
Yes.
on one side you're right on the edge, and on the other side you have a huge space.
Yes. Yeah. So I think it's both those things, right? The size of the nanodisk, okay, varying 30%, and that you have the protein maybe on the side of the nanodisk and this symmetrization thing happening. And so this causes problems for this method in general. And that, yeah, we haven't found like the greatest way to solve them other than one of the things we're trying now is just have a smaller nanodisk so it's like more tight around the protein so that we don't see it as much here. Or using micelles, which is fun to encourage people to.
It's much more homogeneous than the bell size.
Yeah. Yeah, so those are the kind of the two things. And I think this is fun to think about how you actually optimize your experimental design to capture heterogeneity, especially in the context of membrane proteins. Just going back to your detergent micelles, even though it gives you, has other bad things going on, but it can be worth it. Okay, thanks. Yes, and then another thing to consider when you're using these heterogeneity methods is how much of your data to use. Obviously, you want to get rid of the junk that's not folded protein at all or that's just ice, but how much do you want to look at a subset of your data? And I think the most important thing here is to get rid of any residual compositional heterogeneity. As I mentioned, we found that CryoDragon can get confused when there's both compositional and conformational heterogeneity, which surprisingly happens often that you have both, and this can get very tough to tease out from these methods. And maybe something that we also need to do better methods development on how to solve these both simultaneously. But then another thing was that intuitively, we had thought at the beginning of some of our efforts on this that we want to sample our particles as widely as possible, and that we would see differences in heterogeneity if we looked at really what is the most high resolution subset of particles we can get at. And in practice, at least for some of the proteins we're looking at, it's okay to look at a smaller number of particles. We haven't seen too much of a difference when we expand our particle set, but I think this is definitely something you need to consider for your own molecule. What is the right thing to do in terms of how many particles to really bring in? And one thing that we found was interesting to think about while thinking about this was this Nature Communications paper that just came out which presents this method called cryosieve. And it actually is able to, with a fraction, like a quarter of the number of particles, give you the exact same resolution structure. And part of what they're doing here is just giving you what we believe. I think they still actually don't know exactly why it works as well as it does, but give you higher information particles within that subset. And we've run this through some of our data sets and see that after we filtered with cryosieve, we still see the same amount of heterogeneity. So this is something, maybe you don't need to think about this too carefully, but it's something that we've been thinking about, and I think it's interesting in general for the field to think about how tools like this can affect how we think about heterogeneity and how we think about especially data collection for heterogeneity. Yes, so I have no idea how I'm doing on time. But, yeah, so I think the last section I have is combining cryo-electron microscopy methods with molecular dynamics simulation, which I've dropped some hints at before this. But one thing that is a fun vignette to think about here is how much do we actually worry about the cryo of cryo-EM. And this is of particular interest to me because I often think about these temperature sensors, TRIP V1. And I don't know if you guys already went over how fast we think the vitrification process is, but it's very fast. So we believe that we're approximating the equilibrium ensemble of our molecules during the vitrification process. And in this paper, also from Holger Stark's group in 2010, they show that if you equilibrate the ribosome at different temperatures before vitrification, you do see a change in the conformational ensemble, seeing it spread out at higher temperatures as you would expect. And so this is somewhat encouraging that the cryo part of cryo-EM is still giving us a realistic ensemble of our molecules at equilibrium before vitrification. But there's also some interesting work, basically just this paper from Bach and Grubmuller, which actually look at the potential effect of this cryocooling of the structural ensembles. And they have this somewhat actually reassuring result that when you have an ensemble before cooling, and here they're actually simulating ribosomes in a full water box, the ensemble before cooling, if you cool it gradually, you see a huge change in the conformational landscape. You basically just optimize a single peak. But if you cool it very quickly, then you see much more of the other conformations in your state. And so this is reassuring to those of us who are interested in the more lower-lying states in our cryo-EM ensembles. But I think there's still a lot of work to do, both experimentally and computationally, in understanding exactly what the effect of the vitrification process is on our ensembles. So another thing that we can do with molecular dynamic simulation is actually more related to my work that my colleague at the Flatiron Institute is doing. So Pilar Cosio has this Bayesian inference framework for thinking about cryo-EM, where we can basically think about what the probability of a single atomic model is for being in our observed cryo-EM data. And with this, we can do simple studies like take two structures and see what the rough population is. And here we're looking at these specific atomic structures. We're not looking at reconstructed volumes. And this is a nice way to really go directly from atomic structures to the particles themselves without having to go through modeling things into volumes. And with this framework, last year we have a paper that came out where we actually look at how you can compare an ensemble from a molecular dynamics trajectory with an ensemble from a cryo-EM data set. And right now this paper in JPhys KMB is done on simulated data on a fairly theoretical ensemble, just this small chignolin molecule. But it's a proof of concept that we believe will translate well to even larger systems like those we're interested in here. And just to give a quick cliff notes of what this paper shows is that we had molecular dynamics ensemble. Here's a free energy landscape that shows the RMSD to the folded and unfolded state. Here, down here, you have just the folded state, which is the most populated state. Here's a misfolded state, and then the rest of this is totally unfolded, this orange conformation here. And what we did is we took another data set and made synthetic cryo-EM images. And in this scenario, we don't have any of this misfolded state, and we see some other differences in this unfolded population. And we can see that we can re-weight our cryo-EM images by our, sorry, other way around. We can re-weight, so we have our MD simulation. We can re-weight these by our experimental images. And we can see that we see this down-weighted population here. And this is a way of taking a large conformational ensemble and trying to see what structures of those that you have are actually present in your cryo-EM data. And you can see this can work with even a large ensemble of structures. Though this is a somewhat idealized case where we're using simulated data of this molecule. Yes, and this is actually, so molecular dynamic simulations are actually closely related to these questions around how we can assess the performance of continuous heterogeneity methods in SPA. And so there's not lots, but there's a few interesting papers now thinking about ground truth data sets for this. One is here, this paper with Evan Zeitz and Joachim Frank, where one of the systems they're looking at is this HSP90 with this very simple conformational change, and trying to see how well, in this case this was the manifold embedding method, how well it's able to recover the ground truth of this conformational change. And here this led them to develop actually another additional add-on to the manifold embedding method. But this has actually been something that a lot of people have been thinking about, and especially, so I don't know if people have seen this, but DeepMind had, in addition to TikTok, apparently had a journey also into this field of continuous heterogeneity in cryo-EM, also using something very similar to CryoDragon with their VAEs. And in this case, they actually used data sets from Folding at Home, which is a distributed computing resource that allows us to run molecular dynamics simulations on donor computers. And here what they actually did is they took part of their atomistic machine learning framework from AlphaFold and put in more of the cryo-EM machinery. But they wanted to see how well they could recapitulate the molecular dynamics landscape given from the ground truth landscape of this molecular dynamics data set, how well they could recapitulate that with their cryo-EM data set, with their cryo-EM VAE, sorry. I think this was relatively early on, 2021, so right around, when CryoDragon first came out. But this is just still a preprint. They never actually continued this work any further, partly because this result was not very good. They were not really able to do a very good job of getting the same distributions from their VAE from cryo-EM, from continuous distributions. But I think this is a nice example where early on they were using these molecular dynamics simulations as their ground truth. So in trying to think about how to get ground truth for these questions, there's also thinking about experimental data sets. So are there ways to validate the conformational changes we're seeing in cryo-EM with other experimental methods? And in this case, we also want to, there's some nice work from 2015 comparing cryo-EM distributions to SM-FRET distributions. But I think there's more work to be done, especially in this question of how much the vitrification process changes your ensemble, and really looking at both of these approaches to thinking about this question. And I think that actually this review I mentioned in one of the first slides from Nina Milani's group talks about how a lot of these machine learning methods evaluate their performance on synthetic data, whereas synthetic, we don't actually know how to generate great synthetic data for cryo-EM. We have a lot of the statistical concepts, but the noise can still have lots of peculiarities. And so understanding the sim to real gap is still something that is of interest to those of us thinking about these computational problems. And one of the approaches that we took to try to address this at the Flatiron Institute was last year we had a blind heterogeneity challenge where we took a data set, a real data set that we got from here, from New York Structural Biology Center, and also took basically the same molecule and simulated with molecular dynamics so that we could have a ground truth states and their distributions, and then put these two data sets out there for people to analyze. And we got, so this movie isn't working as well as one might like, but basically you can see that these are 9 of the 13 submissions we got back, and people have different kind of results for this exact same data set. And now what we're doing is we're comparing all of these results to each other to see how these different methods performed. And many of these methods were listed in the various methods we talked about in the previous slides. So this has been really fun for us to arrange and see people participate in the community, and results are still forthcoming, but I think it's actually worked better than we thought. And I think it's a small step forward in trying to understand how these methods are going to be usable and trustable by the wider community to really understand how these biomolecules are moving in these continuously heterogeneous states. But I think one of the choices we made for this challenge is something that maybe we can also think about in the discussion session, which is we were interested in having people give us the distributions of the various states in our data set. And I think this is still something that is a question for both continuous heterogeneity and compositional heterogeneity, is how much can we quantify errors in these populations that we get from cryo-EM, get from single particle cryo-EM. So I think there's a few nice examples. Rich's group and Rich in general has done some really nice work on getting these populations from single particle, but also Sandeep Kalandolkar's time resolved cryo-EM paper also looks at populations of different states. But I think fundamentally, these tools are not necessarily built to give you population. There's a lot of stochasticity, especially if you look at some of the things that like Carlos Sorzano has talked about. There's a lot of variability in how an individual particle is going to be classified into these states. So I think really understanding these errors in population is relevant to both discrete and continuous heterogeneity, and I'm welcome for any further discussion on this topic because I think it's very interesting. And then I have a few other discussion topics here if we want to, and that's all I've got. Thanks. Sure.
So you mentioned that when you were processing one of your data set, or at least reading class, you found this computation and you were at first uncertain if it was real or not, and then you found it. Could you comment on that validation process? Was it like computational or
Well, that's a good point. So I think we haven't done any biochemical validation yet, but that would be a next step. Basically, when we're writing this paper up now, is we used every method that we could think of, including some of the ones I mentioned here, but also we also see these same motions in molecular dynamics simulations. And we haven't submitted the paper yet, so I think we're still figuring out exactly what the nuance of the conclusions are. But yeah, it's been a long process, and I hope that not everyone has to do this to just figure out if something they see as a 3D flex result is believable or not. Yeah.
What is it about machine learning and neural networks that makes them so good at like modeling dynamics? Like, what is it that they offer that previous maximum likelihood methods couldn't offer?
Well, I think one thing is that they're explicitly trying to draw this out, especially with CrowdDragon. It has this latent space where it is purposefully mapping a conformational heterogeneity into that latent space. Honestly, I think it's working better than we thought it would. So I don't know if there's a great explanation. I think also, in general, these machine learning tools have been working well on image-based problems. Another thing I'm not sure that can be generally explained on why they work so well there. But yeah. I think that it's also interesting to think about, so a lot of these machine learning approaches take very different approaches, like modeling a deformation field versus just getting volumes in a latent space are two very different approaches, I think, to this question. And I think that one of the things that, for example, we know that people overinterpret latent spaces from variational autoencoders. Like, it is not real space. Like, you cannot really map 2 points that are next to each other. They're not going to necessarily be close to each other in Euclidean space. And so I think Ellen Zong, to her credit, has been very careful about not saying that these latent spaces represent free energy landscapes, because this is something that is not true. Like, you do not have a very sound geometrical relationship between adjacent points in your latent space. But it's honestly a mistake that like a lot of people make sometimes when trying to apply machine learning methods to their dimensionality reduction problem. And I think this is one of the big questions for us of like, how do we use these methods to get out populations, to get out free energies from our cryo-EM data, and I think it's still a somewhat unsolved problem. And it's, maybe it's not going to be solved by machine learning. Maybe something more statistical and Bayesian will get us all the way there. Who knows? Sure. Yeah. So I think 3D VA is super user-friendly and sometimes gets you most of the way there. That's definitely, I don't know, Rich might have more of a practical viewpoint on this, I don't know.
I always start with 3D VA because it's easy. It gives you interpretable results. These other approaches, you need to have a specific reason because it takes quite a bit of work to set them up and run. 3D Flex, we've never gotten to work effectively.
Yeah.
And the other ones, you have to port everything out of Spark GUI and go elsewhere. And often with the sorts of data sets we've been able to find as much heterogeneity as we've tried. We've gone back with CryoDragon a few times, and it can get stuck in certain places because we try to do it in an unbiased way, whereas doing it in a directed way where we're selecting classes can often get us more different states than we can otherwise.
Does that help?
Great talks. You gave, I missed this or something.
That's fine. It's a lot of information.
So you're talking about free landscapes and like how it's related to information heterogeneity. Is there a direct linkage that you can make to the dynamics of your example or like how it's performing its function and these heterogeneous states? Is there a mathematical approach that's going towards that? Or is that the free energy landscapes and I'm just missing that?
Yeah, I mean, that's basically the goal, is to develop a thermodynamic insight of your molecules through building these free energy landscapes. And I think that we're not at a state where we can do that yet, but for me, as I said, one of my interests is in understanding biological temperature sensors, where I think understanding the thermodynamics is critical. I think this approach is going to be an important one for that problem. But we're still getting there. Yeah. Sure.
So this is, I realize that it doesn't have to be your answer to this, but some proteins refold, right, as part of their biological process. And which is like a wholesale change in protein. And I know the papers that you showed, that receptor, that proteins that kind of like pop out. I think that was relatively small.
Yes.
So at this point, what is kind of the I don't understand that, like what you just said is never 100% sure that anything's real. But like what is the kind of cutoff that we can say this is garbage as it relates to size?
So I think the biggest sanity check is, I think, something Rich mentioned, which is taking these methods and going back to your raw particles and reconstructing from those. And I think that's going to be your surefire way to convince yourself that these motions are really there. I think in terms of judging like large and small motions, I don't think that's like the right context, I think.
I guess so
Yeah, go ahead.
I guess I guess another way to reframe the question, if you observe a small motion, are you more confident that that's real than a large?
I think I would be more confident in a large motion. I think actually these methods are much worse at smaller motions in general, partly just because noise is such a big problem in cryo. And the smaller motions may be dominated by noise. But I think some of the most interesting motions, especially looking at like a channel opening up, are actually relatively small. And so I think trying to understand how we can get at those small conformational changes is also a very important part of this field.